I guess we can get started. Happy Friday, everyone. For these short weeks, it awfully seems like a long week, but we made it to Friday, and we're going to finish up talking about, we had one slide left over at the very end when we were talking about different kinds of descriptive research. So we talked about case studies and naturalistic observation and participant observation as different ways of sitting down and actually observing people. And then we talked about the different ways of collecting data. So whether you're observing, whether you're doing like physiological tests, all those different options. But we were left with one slide, and we can talk about surveys. So surveys are questions that are intended to extract very specific information from a group of people. So you can ask people questions, and if you have a good collection of questions and they're all designed to get at a particular question you're trying to answer, it's a really good way to get lots and lots of information. Surveys are really good because they're relatively easy to administer. So if you have a website that's set up and it goes through a whole bunch of multiple choice questions, that's a really easy way to deliver a survey. You can send out thousands of emails by using mailing lists, and you hopefully get quite a few responses. It's also a really effective way to get lots of information because you can ask questions about more than one topic. So typically with a survey, you do want to ask multiple questions about each thing you're interested in because you want to make sure that all of the questions that are addressing that one topic all have fairly similar responses. That's one of the ways that you can account for maybe people not paying attention or giving you bad data or whatever. There's lots of tricky ways you can get at stuff that way, but you can also ask multiple questions about multiple topics, and you can get people to sit through fairly lengthy surveys, especially if you offer incentive. So it's a good way to get lots of information. We just have to keep in mind our limitations here, and of course they're susceptible to biases, and we have a bias from both the researchers and from the participants. So for the researcher's perspective, you can bias responding based on how you ask questions. So if I ask a leading question, it sets you up with either that encouragement to agree or disagree, get you to answer in a particular way. So we could say, you do this thing, right? And then you would want to agree with that because people are social beings and we respond in ways that we expect that we should respond. And then the participants might not give truthful responses. Sometimes they'll do things like click a button randomly because they're not really paying attention and they don't care. Or sometimes they don't want to necessarily have very strong statements. Maybe they're reluctant to agree strongly with a point, so they'll pick with a more neutral answer. Or they'll try to answer in a way that makes them look good. These are all problems that we can have and things to keep in mind. And that brings us out of our descriptive research and into the other type of research, which is experimental research. And so all throughout this chapter, we've been talking about the fact that we can't really have absolute knowledge of causal relationships. With descriptive research, we can find that there's an association between two things, but we don't necessarily get that option to say there's a cause and an effect here. But experiments are when we start changing that. So an experiment involves the manipulation of one or more variables under controlled conditions so that any of the resulting changes in what you're measuring were probably driven by the thing that you've manipulated. And so this lets us say that if we manipulate thing A and it leads to a change in thing B, then changing A causes a change in B. There's a causal relationship there. And when we're doing experiments, we're usually trying to test larger theories, bigger connected ideas, using those controlled experiments. And each experiment is driven by one or more hypotheses. And so we've talked about a little bit the difference between a hypothesis and a theory, but here's our official on-paper concrete definition. So a hypothesis is going to be a tentative explanation or prediction about some phenomenon. So this is something specific where we maybe predict that if we increase the levels of A, then we should see an increase in the levels of B. If A increases, then B should increase too. That's a hypothesis. We predict what will happen if we do something in an experiment. Now, a theory is actually going to be a broader concept. This is a set of formal statements that are trying to explain how and why certain events are related to one another. So the hypothesis is this is what will happen. The theory is why it happens. So you need a base theory, this overarching idea of what you think is going on in that system, in order to start making predictions or specific hypotheses about what will happen. So the hypothesis is the what, and the theory is the how or the why. And this is where I sort of hint, not so subtly, that these are two concepts that have been presented on the same slide, and we talk about how they're the same and how they're different. It might be a good idea to be able to tell the difference between the two of them. There are a couple of those topics throughout this chapter where we can kind of have two nice questions that sort of slide together. So that's the not so subtle nod. So if we're talking about how our theories can lead to those specific hypotheses, maybe we want to make sure that we have a good theory to start with. So what actually makes a theory a good one? So this list here are a bunch of things that are pretty important to being a good theory. We want to hit as many of these as possible, but not all theories will automatically hit all of these. This is just sort of a best case scenario. But the first of our factors that can make a good theory is that the theory should be consistent with prior observation. So what do we already know about the system that you're looking at? So if there's been an experiment that shows that under specific conditions, A causes an increase in B, that's something that we know, and we want to have our explanation take that into account. So having that understanding of prior research and other observations that have been made, our theory can include that, and then it can lead to actual predictions that are supported by what we've seen in other places. We also want to make sure that our theory conforms to the law of parsimony, which you'll sometimes also see called Occam's razor. And this is basically the idea that the simplest explanation is usually the best. And so in the case of theories, we don't know what's actually going on when we start. We don't know how A and B are related, but we have to start somewhere. So let's start at the simplest possible explanation. Let's see if the most direct connection between the two works. And then if it doesn't, we can add complexity as needed, but at least this way experiments start at sort of the same place and we can build up complexity if we have to, but we don't start complex and then try and pare away things to make it simple. It's just easier to go from simple to a little bit more complicated. The next thing that we want from a good theory is for it to be specific. We want to know exactly why A and B are related, because if you don't have those specifics, it can be very hard to predict what will happen. So you need those specifics in your theory to be able to generate good hypotheses. We also want to make sure that our theory leads to things that are both measurable and falsifiable. After making these slides, I realized that sort of the third last and the last point go together really nicely. And this ties into that idea of empirical investigation, where it's something that we need to investigate, we need to have that systematic procedure, and we want to learn based on what we've observed and what we've experienced. So you need to be able to measure the outcomes. If a theory doesn't give you anything that you can quantify, it's not really useful as a theory. The whole point of a theory is that it explains things so that we can use it to make predictions and make sure that that theory is as accurate as possible. But if we can't quantify it, it's of no use. And also, if we can't falsify it, if there's no kind of evidence that could ever be presented that would make us think that the theory is maybe not correct, maybe there's something else going on, if it's something that can never be quantified, that's problematic. So if we look at something like a theory of the existence of extraterrestrial life, we can't necessarily say that there's concrete evidence that they don't exist. We can't physically go to every single star in the galaxy and be sure that there's no aliens there. It's just not a thing that can do. So that's not really a good statement to base a theory around because we can't collect evidence that would contradict it. So for those kinds of statements, they don't really make good theories. And so we want to focus on things that we can have concrete predictions of and can lead to testable hypotheses that we can actually measure and quantify. And then the last of our leftover points is this idea of establishing causality. The whole point of a theory is to try and explain that relationship between A and B. So you want to know if A is causing a change in B or if it's the other way around. Now there's an asterisk here because that's not always possible. It would be nice if we could get causality, but it isn't always on the table. Sometimes the best that we can do is that we're sure that they're related to one another, and that's as close as it's going to get. So now we're going to talk about a couple of definitions, get into some concepts, but you're going to find as we work through some of this stuff, we've actually snuck a lot of these concepts into our vocabulary already, maybe not with their full names, but we've at least talked about these ideas. And so far, I've been talking about thing A influencing thing B. We can actually call those by specific names. And you've probably heard the terms independent and dependent variables before. So our variables are the things that we are measuring or manipulating. And independent or dependent are just telling us about the relationship between them. So the independent variable is the one that is being manipulated by the experimenter and is causing a change, theoretically, in the other variable. I remember this one because it is independent. It isn't changed by anything except the experimenter themselves. The dependent variable is actually a little bit easier for me to remember, at least. This is the variable that's affected by that manipulation. So our dependent variable will change depending on the level that our independent variable is at. So we manipulate our independent variable, and whatever that new level is should cause a corresponding change in the dependent variable. So the value of our dependent variable depends on the level of the independent variable. So we can talk about how does our independent variable affect our dependent variable, or how is the dependent variable affected by the independent variable. And then we also have these extraneous variables, also called confounding variables. And these are just other things that are going on in the system that aren't your independent and dependent variable that can actually affect what we measure in our dependent variable. So I use the example here of our dependent variable. We want to see how much chickadees produce song. We want to see how much singing they do. We'll measure song rate. And our independent variable is going to be time of day. So we're going to look at how much they sing in the morning versus in the afternoon. And from experience, I know that chickadees sing in a dawn chorus. So first thing in the morning, they sing a lot. In the afternoon, they don't sing a lot. So we know now that our independent variable, the time of day, affects the amount of song they produce. But what if there's something else going on that we're not necessarily controlling? What if it takes all year to measure all of the birds that I wanted to study? And so we measure some of them in the spring and some of them in the fall. And we find that the birds in the spring have much different levels from those in the fall. Something else was going on. For those who are curious, chickadees sing a lot in the spring because it's breeding season. and they don't sing a lot in the fall because it's not. And so that can completely throw off your experiment if you don't control for that. Ask me how I know. So with these confounding variables, it's other stuff that can change your interpretation without you meaning it to. So what we thought was lots of singing in the morning, not a lot in the afternoon, gets a lot messier if there's something else varying in the background. All right, so next is another of those really convenient two related topics on a slide. And so we're going to look at the difference between a population and a sample. And again, these are concepts that we've already kind of talked about, just not concretely on one page. So a population is the entire set of individuals that you want to make a statement or conclusion about. I would like to study some kind of perspective from all university students all across North America. That's my population, every single university student across North America. Now, that's not a viable group to study because I can't necessarily survey every single university student. So instead, what I would do is draw a sample or a subset of individuals from that population and include that representative group from the population in the experiment. The idea here is that if I can draw a representative sample, if I can get a subset of people who kind of matches the overall group enough, I can draw some conclusions about my smaller data set and hopefully make some connections back to the group as a whole. So the idea here is that we can generalize our results from the smaller test group to that population of interest. And so when we're looking for these representative samples from the population, there's a bunch of different ways that we can choose those participants. And so we're going to talk about a couple of the most common ways to sample, and some of them are better than others. So the first of these is simple random sampling. And this is one of the most desirable ways to do it. So in this situation, everyone in the entire population has an equal chance of being selected for the sample. So we have a database magically that has the name of every single university student in North America, and we're going to use a random number generator to select 1,000 of them. And that is a perfectly random selection, so simple random sample. What we sometimes use is a sort of a sidestep from simple random sampling, and this is called stratified random sampling. And this is used specifically when one of the groups of interest is very small. And by chance, smaller groups tend to be easily missed or underrepresented in a sample. So let's say I want to look at something about language and how that affects the perspective that I'm interested in. So in North America, most universities are English, but there are some that are French. But if I was only taking a sample of 1,000 students, I might not happen to draw anyone who goes to a French-speaking university. But I really care about French-speaking students, so I would like to make a special setup so that I'm sure that I have a proportional number of French-speaking students. So I would stratify or divide up my population into those subgroups of interest. So maybe there's 98 English-speaking universities and 2 French-speaking universities. So I would set it up so that 98% of my sample would come from those English-speaking universities, and 2% would specifically be drawn from French-speaking universities. So I've intentionally divided up that population and sampled randomly within those divisions, but that dividing up or stratifying the population ensures that what I've selected, especially in those smaller groups, doesn't have unequal or sort of wonky representation. So with a lot of statistical things, especially with small numbers or even small samples, you can end up with a pretty biased sample just through chance. So this helps us avoid that as much as possible. Next, we can look at non-random samples. And actually, our fourth option, a convenience sample, is another type of non-random sample. There are probably way more non-random sample variants than random samples, but they're listed here because these are sort of the two most common big categories. I just found it a little bit misleading because it's convenience sampling is not something separate. But on that note, non-random sampling is just there are not equal chances for everyone in the population to be sampled. So this usually happens due to some kind of study constraint, mostly because it's almost impossible to do a properly random sample. There is no database of all university students in North America. That is a massive privacy problem. So that doesn't exist. So we have to find a sort of a best case scenario, an alternative that gets us close. So most of these will be non-random because they can't. For the purposes of this course, we will use idealistic situations like that theoretical magical database with everyone's info that we can pull from. So we can have theoretically random samples. It's just a lot less likely in the real world. One of the more common types of non-random sampling that I've experienced is snowball sampling. So that's when you're looking for a very specific group that is very, very rare in the population as a whole. So maybe you only want to look at individuals who have family members with cancer. That's a very specific group. And even if you randomly sent out emails to everyone in the city, you might not get a response from anyone who meets those criteria. So a better case would be, why don't you go to a local support group for families with members who have cancer? See if anyone there is interested and ask them if they know anyone who would also fit the study. So you ask them, they find people, you ask the new people who find more people. So that's that snowballing effect. And so it's not a random way of getting participants, but sometimes when you study something that rare, it's the only way you can get participants. And so we find that a lot of our non-random methods are, this is the best that we can do. We know it's not statistically ideal, but we needed some way to study people. And that kind of leads us into convenience sampling, which is a type of non-random sample that's specifically you're working with whatever you have available to you. A lot of research is convenience sampled using first-year undergraduate students at universities because it's a convenient population. So we need to keep that in mind. So how did these researchers draw their samples when we're looking at the conclusions that they're trying to make? Because a random sample is going to give us a much more representative sample from that population, whereas a convenience sample is biased in some way. And we want to keep that bias in account when we start making conclusions. So it's important to note if you're reading research or doing research. And so we have that representative sample is when your sample actually reflects some important characteristic of the population. So does it have the right proportion of English speaking and French speaking, or whatever it is that you're interested in? And you can obtain representative samples using random sampling, or one of the subtypes of random sampling. And for those who are visual learners, we have here a breakdown of a larger population with A through 8 groups in that particular proportion. And at the bottom, we have a representative sample that was drawn from that population. And our representative sample, the pie slices are the same size. So it matches. It represents the population. It does a good job. However, the one on the top is an unrepresentative sample. So that one, group A, is massively overrepresented. We don't know why, because we don't know how they collected these samples. But we could make some guesses if we knew what their experimental procedure was. Maybe group A is just a group that's a lot more susceptible to the type of marketing they use to get in subjects. Maybe they put flyers up at bus stops, and so they got a lot of university students because university students tend to cost more. Who knows? There are lots of ways that a sample can get biased, That's our job to start thinking critically about what might they have missed when designing these studies. And I've already kind of said it, but it's not always possible to randomly sample. Sometimes you just design your experiment and accept the fact that you can't randomly sample. Sometimes you use that as sort of a knowledge that, okay, we can make conclusions about this specific sample, but we can't generalize it to the population as a whole because our sample wasn't representative of the population as a whole. So maybe you've done research and you've only looked at undergraduate students. So you can say that this holds true for undergraduate students, but more needs to be done to see if it applies to everyone. Does it also apply to middle-aged individuals, elderly people, children? Does it apply to everyone? We don't know. And so this limitation can be okay in a couple of different situations. This is where that critical thinking comes into play. The first is if the similarity of a sample and a population doesn't matter. And these are situations where it's sort of like a special case. Maybe you're looking for, you want to show that something is possible, period. You don't care about how common it is or what's the rate of occurrence or any of that. You just want to show that this is a thing that can happen. So if you find one person who meets those criteria, then you have your proof. You've shown that this can happen. So it doesn't matter how you found that person because the fact that they exist is sufficient. We can also have cases where maybe you accept that your experiment is limited because I was only able to look at university students in Edmonton. And I want to make conclusions about all university students, but I only had what I had. However, other experiments have been conducted using similar methods, and they found similar results. So maybe there's a lab in Nova Scotia. They conducted the same experiment on their undergrads, and they got the same results that I did. And there's another lab in Texas, and they conducted the same experiment and got similar results. So we can take the fact that multiple places on very different samples got exactly the same results, and that gives us a little bit more confidence that what we found actually applies to the whole population, which we couldn't have concluded just from our study. But if we use something like a meta-analysis, where we bring in multiple studies, sort of pool all their data and start making conclusions that way, that's a good way to get a lot more confidence in the visibility of your outcomes without having to do all of that research yourself. Then the last one is sometimes the similarity of a sample and population is just reasonable. So maybe you're studying something about gross brain anatomy. You just care about the shape of structure or something like that. And from other studies, we know that most human brains are fairly similar, not a big deal. So finding a human brain is sufficient. I don't need more than that. I don't need to find a random sampling of all humans. The closest 10 humans will be sufficient for me to show that this thing is in this place. So that's another way that it can be okay. And so when we're looking at some of these situations, sometimes you'll think critically about what is the setup, what do they do, how do they do it? Is that okay for us? All right, so that's our basic setup there. Now we're going to get into actually conducting the experiment. And I'm going to talk about like the simplest version of an experiment. So we'll talk about the simplest way, and then as we get comfortable with that, we'll talk more about some of the variations that we can have, sort of add levels to it. But at the most basic point, an experiment is going to look at the comparison of levels of that dependent variable in two different groups. Our two different groups are the experimental group and the control group. So our experimental group are subjects who receive some kind of special treatment in regards to the independent variable that we're interested in. And then our control group are going to be a similar group of subjects, but they don't receive that special treatment. So maybe our experimental group receives a drug treatment, and we want to see if getting that drug changes their mood. And because we need to see if there's a change, we would like to compare their mood to individuals who didn't take that drug. So we're comparing between groups. Sometimes you'll actually see a control group called a comparison group because that's what you're doing with them. For our logic here, we're saying that if everything else is held constant between these two groups, if we can control all the background stuff and manipulate the independent variable so that this group has a different level of the independent variable in this group, drug versus no drug, then any difference that we observe between those two groups should be due to that manipulation. Now, I want to take a second here to talk about how we make sure that our two groups are comparatively similar. And this is through a process called random assignment. This is another one of those things where you want to make sure you know the difference between random selection, which is how we select people from the population for a sample. And random assignment is once you have your sample, say you have 100 people that are going to participate in this theoretical drug study, we're going to have half of them put into the experimental group and half into the control group. And we want to do that in a way that controls for all the extra stuff that might be going on. So for the same reason that we used randomness to choose our sample, we want to use randomness again to assign that sample, each individual, into one group or the other. We don't want to use something that might interfere with what's going on. So maybe you were doing something in a bad case where the first 50 people are your experimental group and the second 50 people are your control group. Well, maybe the first 50 people are the ones who are really excited about the research. Maybe they're really keen on it and they're excited to be here. And maybe the people who were later weren't as excited and they're just here because. There's now some critical factor that might differ between those two groups because they've been intentionally divided based on some other factor. And we don't know how that factor might affect their mood in that experiment. So we use random assignment. We flip a coin for every person that comes in. Or we use a random number generator to assign people to one group or the other. By having that random aspect, we would hope that people should be distributed kind of equally between based on any factor that we're not really considering. And as a good researcher, you might want to take a step back and double check that there's nothing dramatically different in your groups. Why, if you ever do participate in research, they usually ask you questions about, say, your age, the languages you speak, where you're from, like all of those things. Anything that might be relevant, they ask questions about so that they can measure it. And as someone who's inclined to do statistics, if you have that information, even if there is a bias, say one group happens by chance to be much younger than the other group, you can control for external factors if you have enough data points. So it's kind of good to keep that in mind. And you might already be thinking, well, if we're doing something to the experimental group and we're not doing something to our control group, isn't that an extra variable that we need to think about? And that's where the placebo effect comes into play. So this is when the effect of a treatment arises not from the thing that you've done, but from the patient's expectation of what it should do. So if the experimental group receives a drug and the control group doesn't receive anything, then the experimental group knows they're in the experimental group and the control group knows they're in the control group. So maybe the experimental group think this is going to help, and because people are very responsive to things like that, they might start feeling better just because they expect to feel better. And similarly, the control group might feel maybe even worse because they know they're not in the experimental group. So humans being reactive and troublesome to study, we might want to use an actual placebo treatment where we hide what group they're in by giving them something that looks like a treatment but isn't. So if we were giving the experimental group a pill that contains that experimental drug, maybe the treatment group or the control group receives a sugar pill. So they still get a pill, they don't know what group they're in, but it has no chemical effect. Or if our experimental group is receiving an injection of a drug, then we give the control group an injection of saline. So they still get the injection experience and anything that might come from having gotten an injection, but they differ only in whether they got the drug or not. So that's something else that we want to keep in mind and try and control for. You'll find the repeated phrase here is that we're controlling for absolutely everything that we can, and we're just starting to think about ways to counteract stuff that can go wrong, really. All right, so next we're going to start talking about some of those variations. So we talked about our very basic two groups, comparing between the two groups, saying, what else can we do? And I'm actually going to hop to this next slide that shows the difference between what we've been talking about already, which is actually a between groups design or between subjects, where you have one group that was given the treatment and one group that was given the control, and we compare that dependent variable measure for both. And then we're going to mix it up a little bit. What if, instead of having two separate groups, what if you only had one group and it received both treatments? What if they got the placebo and they got the experimental treatment? And that's when you get a repeated measures or within subjects design. And that's because instead of comparing between two different groups, you're looking within a single group. You're looking at them having experienced multiple things. So I have a visual for this. In our between groups, we have group 1, they receive treatment 1. Group 2 receives treatment 2. We compare the group averages. Repeated measures, we have one group and only one group. And they'd receive treatment 1 first, and then they'd receive treatment 2. So whether that's experimental and then control, or control and then experimental, that'll depend on your setup. Now, for good science, you would want to consider something like order effects. What if receiving the experimental treatment first somehow changes your biology? What if there's something going on? Again, we're thinking about worst case scenarios. So usually what you would do is have half of your group get treatment 1 and then 2, and half of them get 2 and then 1. So you just control for extra stuff. But that's just sort of mentioned because some people wonder about things. So for our benefit of actually having a repeated measures setup at exposing a group to more than one condition, that helps us control for extra variables. Because instead of looking at the fact that we hope that group 1 and group 2 are the same on all those background factors, we're just using the same people. The same group, the only group, gets both treatments. And so in effect, each individual gets to act as their own control. So there are no extra variables because you're comparing them to themselves. That's really useful statistically. It's also beneficial because instead of having to populate two separate groups, you only need half as many people. You only need one group because you're comparing them to themselves. So that can be beneficial if it's really hard to find participants. So our next variation is, okay, instead of one independent variable and one dependent variable, what if we have more than one of either? So we'll start off with, what if we manipulate more than one independent variable? So we can have two things that we are going to change or control as the experimenter, and we're going to see how changing both of those things influences our dependent variable. And this is really useful because it actually lets us look at interactions. So instead of just looking at IV1 and IV2 separately, we can even look at how they affect each other. And because behavior is very complicated and in the real world there's lots going on, being able to look at those interactions actually gets us a more full picture of what's actually going on. And I have a neat little experiment example that we can talk through for this. And so for this setup, they were looking at the effect of distracted driving on driving ability. So for the first setup they did, they had one independent variable that was you're talking on the cell phone or you're not talking on the cell phone while driving in a VR simulation. And they measured their dependent variable here was how quickly quickly you would stop when something showed up on the screen. So how quickly can you brake to avoid an obstacle? So our dependent variable there is just braking speed, or what do they call it, reaction time? So a longer reaction time means it takes longer to stop, which is bad. So they do the basics, distracted driving versus not distracted driving, and there's a slight difference where if you were on a cell phone, you took a little bit longer to stop, but it wasn't a huge difference. So they wondered what else might be influencing this. And so they introduced another variable, and that's this one here, independent variable 2, and that's traffic density. So what happens if there's lots of cars on the road or no cars on the road? And so they ran it again. So you have low traffic density, high traffic density. Are they driving, or are they driving and on their cell phone? And at the bottom here, they've broken it down so that we can see high and low traffic density, distracted driving, not distracted driving, for both of them versus their braking times. And so we can see that there's actually a difference between the low traffic density and the high traffic density sets. So in low traffic density, the distracted drivers take a little bit longer to stop, but not a lot. But in high traffic density, the distracted drivers take a lot longer to stop. And because that difference between the sets of bars is different between those groups, we see an interaction where distracted driving is more detrimental, specifically when there's high traffic density. So we wouldn't have known that there's an interaction if they had just tested high and low traffic density and just tested distracted driving versus not distracted driving. But by testing both together, we get that more full picture. And then the last of our points, which is not, oh, no, there. The last of our points is just that we could also measure more than one dependent variable. So instead of just measuring reaction time, maybe we also wanted to look at how often they check their mirrors. Or maybe we wanted to look at how variable their speed is. By checking multiple things, we get a better feel for what's actually being influenced by that independent variable, and again, gets us closer to seeing things as we would in nature. And then our last slide for today is all about the advantages and disadvantages of experiments. And the advantages, the big one, is that we can make conclusions about cause and effect relationship. This is one of the only ways that we can reliably get that idea that changing this variable causes a change in that variable. The disadvantages, as we just said, when we're controlling all of these extra things, when we're only looking at one thing at a time, we're really far away from how things are in nature. In nature, things interact, there's lots going on, and it's really hard to pull out what might be influencing behavior. So we need to keep that in mind when conducting experiments, that we're only looking at, say, one or two variables at a time, whereas in nature there can be hundreds. So we're limited based on what we can study at any one time. There are also some ethical and practical issues with experiments. There are some things that you cannot assign people to, and there are some things that you should not assign people to. So, for example, you cannot assign certain children to grow up malnourished if you want to study the effect of malnourishment on intelligence. You'd be stuck with descriptive studies. You'd have to look at people who happened to grow up malnourished and see if there's any correlation between their metabolic intake as youngsters and their IQ as adults, but you can't manipulate that. It's not ethical. And there are other things where you just physically cannot change, so we'd have to find an alternative. And so those are some of the things we want to keep in mind when we think about experiments. And that's going to let us start moving off into what do we do with our results? What do they mean? Do we trust them? What do we do next? And then a little bit of statistics on that side of interpreting results as opposed to actually doing stats. But I will leave us here for today, and I hope you all enjoy your weekend.